so I've already gotten all the quantum information. But this is actually something quite different. And it's a very vibrant field nowadays, right? It's basically whenever you read about something in the news about like quantum computers or something like that, that's quantum information, right? And it's also a field that I find is very plagued with sort of misconceptions. It's sort of up there with like planets, where people are like every planet is habitable. Similarly, people sort of claim all sorts of random crap about what it is and that quantum computers can do. And usually people who write those kind of articles don't know what they're talking about. So I'm hoping to dispel some of that while also giving you some intuition for how does quantum mechanics works in this sort of applied context. And so a quote here is this quote called, which is just spooky action at a distance, which some of you may or may not have heard before. That will make a little bit of sense maybe a little bit later in the lecture. So let's talk about a normal computer. How does a normal computer store information? Well, like the fundamental unit of information is something called a bit. And a bit is essentially like in binary, like it's either a 0 or a 1. I don't know if you know this, but your computer basically stores information fundamentally as like bits, in the sense that it's just a whole bunch of zeros and ones, which is really like, at a microscopic level, like a transistor having a certain voltage or something like that. It's all stored in this particular way. And just having enough bits, like you're able to store the information that you want. Right? This is how a normal classical computer works. In quantum computation, the answer is a little bit, what we deal with something a little bit different. We have something called a quantum bit. Quantum bit. And this is not usually the word people use because it's kind of long, so people just say qubit, which stands for quantum bit, as you can see. And so I can write sort of like, it can be in the state 0, and I'm just going to put like this like little symbol here, but really it's 0. It could either be in 0 or it could be in 1. But I don't know if you remember this from last time, is that in quantum mechanics, states can actually be in superpositions, right, of two different states, right? So not only can you be in like 0 and 1, you can also be in some combination of 0 and 1, right? Superposition. So in particular, you could have like an equal superposition of 0 and 1. You can be in both 0 and 1 at the same time, okay? Or for example. Or you could be in like 0 and 1 at the same time, but like there's a minus sign here instead. Or you could be in like mostly 0, but like a little bit of 1. You sort of have a lot of, you sort of can see that even though like qubits seem very similar to bits, there's something very strange going on in the sense that you're sort of allowed to be in more states than 0 and 1. You sort of have like an infinite number of different states you could be in, right? There's like infinite number of combinations of 0 and 1. This kind of system is called a two-level system. It's called a two-level system because there are sort of because there are two of these. There are like sort of two fundamental states called basis states, right? And you can sort of any other state can be written in terms of these two. Right? And so why do I sort of point out that two-level systems are a thing? Well, the thing is that they occur frequently in nature. Right? The idea of having states which are sort of in two, like systems that can only be in two different states, right? In the sense that even if a system has more than two states, usually you can sort of like mess around with the system so that only two states are really realistically possible. For example, if you have an atom, it has a whole bunch of different electronic states. You could, like, for example, make the energy low enough so that the atom could only be in the bottom 2 or something like that. And so really, as long as you can find like a viable two-level system, you can like try and make a quantum computer out of that. Okay. So what is it that a quantum computer can do? I haven't really explained why it is that this would be useful, right? Why would we want to make a quantum computer? Our iPhones seem to work pretty well. Well, let's sort of give you the canonical example. Suppose you were a bank. This is a bank. It's got like a roof, and they've got like money or something, and they would like to make sure nobody else gets that money. And so how does what is it that a bank needs to do, right? Well, people should be able to make deposits to the bank or make withdrawals or do something secure to the bank, right? They should be able to send messages to the bank that no one else can read. Do you agree with me? Like, you don't want people reading your private bank transactions, right? In particular, if somebody like taps the wire that you're using to send your signal to tell the bank what to do, you don't want anyone else to be able to read that, right? So you want to be able to like encode it somehow, right? The problem is anyone should be able to send a message to the bank. Do you agree with me? So then how are you able to like sort of tell everyone how to encode their messages, but also make it impossible for them to read the message afterwards? And so one very popular way of doing this is called RSA. And this is basically like three people's names. But the basic idea is this. There's some like, I don't know if you guys know about prime numbers. There are sort of some numbers which are like cannot be factored into other numbers, right? Like for example, 2 cannot be factored into other numbers besides 1 and 2, or 3 or 5, and so on. And there's actually an infinite number of those. Okay. And so in particular, what you can do is you can take two really long prime numbers, I'm talking like hundreds of digits long, you find these somehow, you multiply them together, and then you give that number to everyone. So you have like a hundreds of digits long composite number that only has 2 factors, besides itself and 1, right? Like so you have like this huge number. What's the idea there? The idea is that, I'm not going to go over how this works because it's probably a little bit nuanced, but the idea is everyone knows the big prime number, and so using the big prime number, they can encode their message. But they're not able to decode it unless they know what 2 numbers you multiply together. You see what I mean? Now you might say like, well, that should be pretty easy to do. You just get a computer to figure out like what numbers multiplied together would equal that big one. But if you think about it, it takes a long time to check those numbers, right? Like you basically have to like go through like every number from like 1 to like square root of this hundreds of digits long number, and then try and figure out which 2 numbers multiply together. Like which number divides this big number, right? That's like clearly doesn't like, that would take forever, right? And even if somebody did figure it out, you could just make a longer number, you know? The thing is, no one's ever proved that a classical computer couldn't do this efficiently, but people have tried a lot and it doesn't seem to work. So that's basically what your bank security is resting on. However, quantum computers sort of win out in this regard, right? Quantum computers have been shown to be able to do this in a theoretical context, but no one's ever actually done it because it sort of takes a big enough quantum computer. But someone named Peter Shor made something called Shor's algorithm. And if you had a big enough quantum computer, big enough being like imaginable quantum computer, it could actually sort of break this problem and then destroy your bank security. So you'd have to find something else to do. And so what's the deal there? Well, the thing about quantum computers is that they're sort of like parallelizable, right? In the sense that because you can put your quantum computer in a superposition of a bunch of different states, you can basically like sort of run a whole bunch of things sort of in superposition, and then sort of at the end interfere all your states back together, and then get some answer. And you might have to like run it over and over again, but it's still oftentimes much more efficient than actually just running classical computer, right? And so a rough estimate for how powerful a quantum computer is, and this is very rough, is if I have n number of normal bits, that's going to be equivalent to log of 2 of n, like so little n qubits. And so I don't know if you guys know, like log is basically sort of like what power do you need to raise 2 to, right? In order to get n. You can see that if this is like this is sort of a rough estimate. If I had this is, let me think of an example here. If I had like 10 to the 24, let's put it this way. If I had like 2 times like 2 to the 100, right, normal bits, that's like a lot. I don't know what that number is, but it's like a lot. For example, like 2 to the 3rd is like 8, which is about 10. So then like this is about 10 to the 30, like within a factor of 1,000 or something, right? That's like a lot, you know. But how many qubits would that be? 100. So you can see how much you win, right? With quantum computing. This is sort of a naive estimate for how powerful this would be. So you can see that at some point we're going to reach something called quantum supremacy in principle. And so actually recently Google has claimed that they have reached this kind of thing. It sort of can be defined in many ways. Sort of has the picture of being like, hey, like, you know, our quantum computers are like good now. But really what it means is like your quantum computer can outperform classical computers. And in the most recent context, when you read about it, it really means that a quantum computer has been able to solve some problem that a classical computer could not have solved. Technically that problem, well really that problem wasn't very interesting that Google solved, but technically they solved a problem that a classical computer couldn't solve, so they get like brownie points for that, I guess. So what do you need a quantum computer to do? What do you need for a quantum computer to happen? So there are these things called the DiVincenzo criteria. Criteria, which are basically a list of things that you would need a system to, you would need to be able to control about a system in order to make it into a quantum computer. So first, you need a qubit. So like you need to define what physical system is your qubit, which seems kind of obvious. You have to figure out what is it, you know. And then after this, you need to figure out how to scale it up. So not only do you want one qubit, obviously one bit is not going to help you very much. You need like many, many bits, and you need to be able to figure out how to like work with all of them at once, right? Which is not necessarily easy. You need to be able to start off your qubit in a state. Because in order to do a calculation, you sort of need to know what your system state is, right? So you need to be able to sort of control what it starts as. Let me see. You need to be able to you need to be able to do your calculation before the qubit decays or before the qubit sort of gets pushed around by its environment and sort of forgets like what it's supposed to be doing, right? So like do calculation faster than quote unquote decay. You also need to be able to measure the qubit. It's kind of important. You need to know what your computer's saying. And yeah, also one thing I forgot is you need to be able to change the state of your qubit. You need to be able to modify the information that's in it. And these seem like pretty straightforward things that you would want out of a normal computer, roughly speaking. One thing I didn't mention is that because quantum computers sort of put everything into superposition, right? You basically like you can't check the work of a quantum computer because I don't know if you remember this, but last time when we looked at the double slit experiment, if you try and figure out which slit the particle goes through, then the entire pattern gets changed. You can't really know anything about a particle until you measure it, and when you measure it, you change the system. So you can't really like measure different things about your quantum computer. You just measure the end, and then you sort of everything else gets modified, right? You can't really check the work of a quantum computer. Yeah. So let me see what else there is. Yeah. Yeah. So if you really think about it, I erased this thing. Okay. I told you that a quantum computer can be in any one of an infinite number of different kinds of superpositions between 0 and 1. That makes it sound like that there's an infinite amount of information that could be stored by a qubit. To see that, I could be like, well, maybe make the second digit like all the digits of pi, right, or something like that. Like make them weighted in such a way that like every digit of pi is stored on the qubit. And that's technically true, but the thing is, once you measure the qubit, you sort of destroy all of the information except for one classical bit's worth of information. So you just want to sort of, the way that quantum computers work is you basically don't want to measure the quantum computer until the very end, because measuring it at all and in between will sort of destroy any information you have, right? Which is, makes coding with a quantum computer a unique challenge. Like it's not like coding with a normal computer for sure. It's very strange. This bank is getting erased because physicists don't get money. Let's talk about some properties of quantum computers, what they can and what they can't do. So one critical property is called unitarity. It's very important for quantum computers, and to sort of explain why, let me write down a sentence. Okay, so this is like a conjunction, right? This is sort of like what's called a gate, right? A logical gate in like classical computing. Okay. So Alice is happy and Bob is sad. Suppose that one of these, suppose that this entire statement was false. Okay. Like this statement is not true. Okay. Now, let me pose to you this question. Is Alice happy or sad? You guys know? Can you figure it out? No, you can't, right? Because it could be the case that Alice is sad, in which case, yes, this would be false. But she could also be happy, but then Bob could be happy also. And this could also be false, right? You can't figure out what these individual things were that went into this gate. So like, if this was like A, and this was B, and this was like sort of and then you get false. You can't sort of like tease back out what A and B are. Okay. So in this sense, like and, but also or, these kinds of things are not invertible. You can't undo them. And quantum computers cannot do those kinds of things, okay? At least they can't unless you like throw away the stuff that makes them useful, right? Anything that you do on a quantum computer has to be like reversible, like according to the rules of quantum mechanics. You can't do things like or and, right? You can do things like not, right? Because if I say not Alice, like Alice is not happy, right? And I said that was like false, then you would know that Alice is happy. And so this kind of thing is allowed. It's sort of a consequence of something called unitarity. But one thing that you might not realize is that there's also something called, in quantum computers, so what would a not do on a quantum computer? Well, it would sort of take 0 and turn it into what? And it would take 1 and turn it into what? Okay. But this is not the only thing that a quantum computer can do. In fact, you will actually play with a real quantum computer in your problem set, because IBM has made, or I think it's IBM has made them public to some very rudimentary ones. But you can also do something called a square root of naught. And what does that mean? It sort of means like if you apply this twice, you get a naught, right? But sort of if you apply it once, you could imagine something like this takes you to one superposition of 0 and 1. And this takes you to another superposition of 0 and 1. Which is strange. In fact, there are an infinite number of kinds of square root of naughts you could do. But now you have all these weird operations. Like now, what does it mean to do a square root of naught in like a normal computer? It doesn't make any sense, right? But like a quantum computer, to a quantum computer, this kind of operation actually makes sense. Like you're sort of taking your qubit and sort of like turning it into like halfway between 0 and 1, right? So you're sort of going halfway between 0 and 1. And so if you do it again, you sort of go all the way. That makes sense. Yeah. And so really like what you lose in unitarity, you gain in like this vibrant series of random gates that you can do. Yeah.
Is this sort of related to like another plane? Because you have all these like square root of 2 and like those sort of
So like broadly, like I'm writing these square root of 2s because you technically need them. Like you don't have to really think about them, but the idea is you can think of, if you want to think about it, you can think of these as like arrows, and then they have a fixed length of 1. But that doesn't really matter. And so how do you visualize what kind of states are allowed? Well, a way of visualizing it is called the block sphere, which is a sphere, right? Where you imagine that 0 is on the top and 1 is on the bottom, right? And how do I think about this thing? Well, it's kind of strange. Why did I do this? Well, if I wanted to do some kind of quantum operation to this guy, it turns out that, like, let's say I wanted to do like this, like a knot, right? That would just be sort of like going from here to here, right? But I could also just go halfway, right, into like square root of 0 plus 1 and this would be like a square root of naught, right? Does that make sense? Like this kind of thing is allowed. And you can see from this picture that you could actually rotate like this too. That would also be a square root of naught, but like a different kind. Or like you could go this way, down here, and then like back around, right? Like this. And so in this picture it becomes very clear that quantum operations are like on a single qubit will look like a rotation. Right? So like essentially the way that you have to think about like things when you're dealing with a quantum computer is like you're dealing with rotations like on this sphere, especially when you're dealing with only one qubit, right? And each of the points on the surface of the sphere is its own like different linear combination of 0 and 1, right? So think about the vibrancy of number of states that you have here. Yeah. And so, yep. Let me heat this up actually. But here's something that is a little bit more interesting. This is sort of a property that I asked Shishir to hold off on last time. This is a little bit of a demo. This is sort of a classical demo, right? People already knew that these things existed. So I don't know if you guys remember, we talked about polarization like sort of randomly and didn't really explain too much what that was. I think it would help if I had a phone flashlight. So what you see here is sort of 3 pieces of what look like plastic, right? Do you guys see? So if I have this piece of plastic and I hold it here, I can put like this piece of plastic behind it, right? But if I turn this, you see what's happened? If I turn this, it will sort of like darken, right? And what's really happening is that these two only let a specific kind of polarization through. You can imagine that the light is sort of going like wiggling up and down or left and right, and it sort of only allows one of those kinds of light through. So if I sort of put them perpendicular to each other, no light can get through. See what I'm saying? However, that's not the full picture, right? Because like we know that light is photons, right? Even though like we heard from quantum mechanics that they're sort of wavy objects, right? And we heard from E&M that they're electromagnetic waves. We still like to believe that they act like particles, but the thing is like there's something intrinsically wrong with that idea. Suppose I have a third one, and I put it in at 45 degrees. I don't know if this is not very easy to see.
Do you want my phone flashlight?
Yeah, no, I have a phone flashlight. Yeah, I think Leon gets it. Let me check out phone flashlight. Okay, you see this? Is it going? You guys see this phone flashlight?
Yeah.
Can you take this out for me? Yeah. What happens? How does that make any sense? I put something in between, and that somehow like makes more stuff go through. Did you see this? You can try. You can play with this. Like I can hand this around here. You can have these. That's sort of like a consequence of waves. So waves do behave like that, as it turns out. But like also like these are particles. So like what the hell is going on, right? And like my claim and our claim when talking about quantum mechanics is that in fact like electrons do that too. Everything does this. Right. Yes.
So is this sort of like a filtering effect?
It is kind of like it filters for polarization, right? What you can think of as happening is that the polarizer measures the state. So it measures the state in this way, and then it measures the state in this way again, and sort of filters out like the one that is measured to be wrong, right? But what you're doing in the middle, if you put in the middle polarizer, is you measure it this way, then you measure it sort of this way, crossed, and then you measure it this way again. But remember, when you measure something, you always sort of change the state. So once you measure this sideways one, you sort of flip the state around, and then when you flip it around again, like some of the state still like goes through, because there's no situation where like they're 90 degrees, right? So not all of it will get filtered out. It's very strange, right? If you think about it, the more you think about it, the more strange that it is, right? Like if you have like a bunch of filters, like these filters are very far apart, right? Like how does the photon know not to go through the first one? Like how does this even make any sense? Like it just doesn't. Also, if you have a laptop, you can actually put it in front of your laptop and you can see that your laptop's light is polarized.
The PSA, if you want to try this at home, like movie 3D glasses are also polarizing filters. So stock up on those and try to observe the effects.
And so, let's talk about quantum entanglement. Maybe I should have shown you this a little bit later. But quantum entanglement is a very important topic because you don't want to just have, I didn't really tell you what it is, but you don't just want to have one qubit. If you had one qubit, that would be very boring. I think you would agree. You know, one qubit, quantum computer can't really do anything. You want multiple qubits, right? And when you go to multiple qubits, you realize that you sort of like win out even more than you think when it comes to quantum computers. Now let me ask you like a classical question that's going to sound very stupid, and you're going to be like, Nicholas, this doesn't, like, how could this improve anything? This is dumb, right? Suppose, pardon?
I don't know. I'm telling him to use a non-polarized source of light. If you use your laptop's light is already polarized. So
so it will be weird. Okay. So suppose that Shishir and Shashank go to the store, but they're really poor, so they can only have enough money to buy one pair of gloves. Not far from the truth. No, I'm just kidding. But they're like both right-handed, right? Are you guys both right-handed?
Yeah.
Okay, yeah. So then they're like, damn, like we can't decide who gets the right glove, because times are tough. So what they do is they're like, okay, what we're gonna do is we're gonna take two boxes, right? And then we're going to put one in each box, and they're identical boxes. I can't tell them apart. We switch them around so that no one can see which one is which. Then we each take one, and then they go to their respective houses because they live separately in this universe for some reason. And then later on, Shishir opens his box. He sees he has the left glove. Damn, right? But then he knows immediately that Shashank has what?
The left glove.
He definitely has the right glove, right? And and this doesn't seem like a surprise to you, right? Like that makes perfect sense, right? Do you agree with me? Like that seems like really boring. That's like sort of the concept of entanglement, right? But like, why is it not surprising in a classical context? It's not surprising because we already know, like, even though you don't know what's in the box, it's already been decided from the moment you guys switched boxes and left, right? Like at that point in time, the gloves themselves knew where they were and had decided which box they were in. But you didn't. That doesn't matter if you didn't, because like it doesn't matter what your opinion is. No offense. But why is it weird in a quantum context? Well, like this does happen a lot, right? Actually, like you could have a Higgs boson or something, which is like a particle that doesn't spin around. Oh god, I haven't explained spin. Okay. You could have a particle that doesn't spin around, right? And then it sort of breaks up into two particles. Now you know from conservation of angular momentum that one has to spin up and one has to spin down. So imagine instead of going to the store and buying gloves, they decide to be a little more sciencey. They buy like spins, like that were made in this way. And they both have a box. They go really far apart. They measure. He measures that his spin is up, and then he knows immediately that Shashank's spin is down. Okay, right? Does that statement make sense? So you're like, oh, well, that's like not very surprising because, the spins already knew what they were beforehand. But like, really, did they really know? Because like in quantum mechanics, nothing is determined, right? It's not deterministic. Like, did it really decide beforehand what it was going to be? And it turns out there's actually an answer to this question, surprisingly. By the way, these two particles are what's called entangled. So their state will look like this. So if you measure one, then you instantly know the other. Because if you measure, if Shishir measures this to be down, then you'll change the system so that it only is this, and then he'll know that Shashank's state is up. Right? But here's the problem with that intuition. Suppose you assume that that there's something called realism. What is that? That's basically the statement that the states themselves decided what they're going to be beforehand. Okay, that's realism. And you assume locality, which is that information can't travel at the speed of light. In other words, like once you separate the boxes, like one spin can't tell the other spin, let's play a prank, like let's like be opposite, right? Like they can't do this. So you assume these two things, which seem very reasonable, right? Like, either like things are determined or like you can't violate the speed of light. If you assume these two things, you can derive mathematically, just from math, something called a Bell inequality. I'm not going to really explain that too much. It's basically like some inequality that you can sort of like, just mathematically, from these two things alone, you can derive that. And then you can go into the lab and show that that is wrong. Okay. What does that mean? It means you have to say goodbye to one of these. Okay. Which one? People have differing opinions. Usually people throw out this one and say, well, nothing in the universe is deterministic, determined. right? Or sometimes weird people throw out 1, 2, 3, so on, or 0, which is the Higgs boson, right? It's sort of like a property of how much that particle could be spinning, basically, right? Even though it's like not really spinning. We'll talk about it in quantum field theory a little bit. But the important thing is that when we deal with quantum computers, people usually like to talk about spin 1/2 systems, because those are the systems that have 2 states. And so really, like, you can sort of think about, like, if you have like the spinning of an electron, that could be like an example of this, right? Like of all of this stuff that's happening. Okay. So we can also talk a little bit about quantum circuits, although I'm only going to do this because it sort of shows up a little bit on your problem set, so I want to make sure you kind of understand what's going on. How do you like entangle states together? Well, you can sort of imagine. So here's the way that so people will draw like what are called like quantum circuit diagrams, where you basically have a qubit and you say like what the qubit starts off as, and you sort of draw a line. And so like the line, it goes right. So right is sort of like, as you go right, more and more things are happening. And so I could have like another qubit, for example. And then like another one maybe. And it could be like, okay, well, you know, I can do things to this circuit. So I could be like, not, right? And then at the end, I can measure it. And if I measure it this, what do you think will happen? If I start off as 0 and I do not, what happens? What do you guys think? If I do a not to a 0, not 0 is what? 1. You'll measure 1, right? And similarly, if I start off with 1, what will I get? Right. So that you know, broadly speaking, makes some kind of sense. What if I did something like square root of naught? What do you guys think? What would I measure? I'm halfway between 0 and 1. What would I measure?
Square root 2, 0 plus 1.
Except remember, you're only when the final answer you get is either 0 or 1. You don't measure 0 and 1. You only measure one of those things. What do you think you would measure? Any ideas? Turns out you would measure like either with a 50% probability. So you literally can't predict which one you would measure. But you know that if you did this experiment a bunch of times, that you would eventually get, you know, like 50-50, right? Now let me consider a different kind of gate. Let's just forget this one for now. There's a gate called a C0 gate, which is basically like this. I draw a plus, and this is gonna be on your problem set, but like I basically walk you through those instructions, right? The idea is this. Okay. The statement is, if this is 0, if the qubit here is 0, then do nothing to this. Okay? If the qubit is 1, then switch this. Okay? So for example, if this was 1, then like these would sort of go here. This guy was 0 and this is 1, which means switch it. So this goes from 0 to 1. You see what I'm saying? This is called a C0, controlled knot. On the other hand, if this were 0, then basically your circuit would reach here. It would be like, do nothing to this, right? Then you would end up 0, and then do nothing is still 0. Okay. And so you can quickly see, if you think about it, that you can reverse this operation, so it's allowed. Okay. But then here's the question that we want to think about. Well, this kind of gate is not the only kind of gate called this, but this is called an entangling gate. It's a gate that entangles two systems together. Why do I say this? Well, suppose instead of applying C0 here, I apply the C0 here. Okay. Well, what happens? Well, you have the state 0 here, then it goes through and it becomes 1 over square root of 2, 0 plus 1, right? And then what happens here? Well, the quantum superposition part of this state, which is 0, says don't do anything, right? Well, the quantum superposition part that says 1 says no, do something, change it. So what do you get? You end up getting a state that looks like this. 1/2, 0, 0, plus 1/2, 1, 1. And what would you actually measure here? Well, let's say I measured both of these. And I can measure them arbitrarily far apart, like one on Mars, one here, whatever, right? And I could be like, I measure this one, and I measure this one. Each of them individually is going to have 50% chance of being in either. However, if I measure one, I automatically know the other one, no matter how far away it is. Bearing in mind that Bell's inequality essentially says, like, it didn't decide from the beginning, you know. They just sort of agree for some reason. And that's pretty strange, right? But this is the sense in which that this data is entangling, right? It causes like quantum entanglement in this way. Spooky action at a distance, right? Yes?
What do you mean by like the 1 0s and the 2 zeros and 2?
Sorry, so 0, 0 means the only possible state of this, if I only had 0, 0, that would mean the state of my system is both are 0. If I have 1, 1, that means both of them are up. But in quantum mechanics, you can be in any superposition of any two different kinds of states. For example, you could come up with a state that's like this, 1, 0 plus 0, 1, in which case you're like, they're always going to be opposite. Or you could come up with like